And the forward model represents maybe the mapping from an input location at a certain location, and like thousand, let's say, output locations. That's a forward model. Suppose we have that forward model. We want to find out the mapping from all the output, if the source is at the output location, and the sensor is now placed at the original source signal, we want to find out what that model is. So if I'm here, I'm the original forward model, I'm here on the source, and you guys are the sensors, okay? That's a forward model. Now I'm interested in a model where you guys are the source, and I'm the sensor. Okay? So it's a multi-input, let's say single output model. So millions of outputs, millions of inputs to one output. So how do we identify such a model? We don't want to do system ID with one input at a time, or even millions input at a time. That's impossible to do. So what we do is we rely on this principle, reciprocity in structural dynamics. It says that if you take the forward model and transpose it, you get the reciprocal model. Okay? So we can turn a one input, a million output model to a million input, one output model by a simple transpose operation. So in the ABC model that you've seen here, for example, you just transpose it, H become A transpose, C become B transpose, C become B transpose, and boom, and we have the reciprocal model. Okay? And why do we need this model? We can use this model to predict the response of if the input is at any one of those million output locations, okay, and the sensor, if the sensor is put at the original input location, we can use that. But more importantly, we use reciprocal models to model the dynamic response to a moving source. So if I have a sensor here, I have a truck driving, I want to model what what the sensor here will receive due to a moving source. Then we use reciprocal model to do it, because the reciprocal model is a million input, one output model. So if the truck is moving, basically it is going from one location to another. So we need a multi-input single output model, and that is a reciprocal model. So we can use this model to model moving source, dynamics of moving sources. So like a tank moving, okay, or somebody walking, how does that register at this sensor? That model is derived from a reciprocal model. So this is an example of using those reciprocal models for moving source simulation. So these things that humans do, they walk, they push wheelbarrows, they dig, they run, okay? So we want to find out, I want to have a sensor over here, and I want to figure out what somebody is doing over there. And so we model the signatures due to these moving sources. So this is an example of a person walking versus running. So when you walk, you would apply a vertical force and horizontal force onto the ground as a function of time. So this is, as a function of time, what the force is for the left foot and the right foot acting on the ground. That's a vertical component. And this is what happen if you run instead of walk. So people who study these behaviors and figure out what the forces are. This is now the horizontal component of the person walking versus running. So once we know these profiles, we can use reciprocal models to simulate what the response will be observed at the central location. And this is an example of a underground network of tunnels. So because sometimes people dig tunnels underground for illegal purposes across some borders. So you can study the ground vibration. Okay, and like I said, if we use the supercomputer model to do this, it would take too much time. So we're going to use the forward model and then use the simple model version of it to do the simulation. And this is an example that shows how good the simulation is. The red ones, the red one is the ground vibration at the sensor location that is derived from the full flow supercomputer simulation. And the other here, the green one, are the ones that we derive from our identification model, the reciprocal model. And the two, this is the plot that shows to confirm that the model that we get is correct, because it's showing overlay of this supercomputer simulation and our model. And here the comparison stops here because it took just too many hours to run this full blow supercomputer simulation. So we can only simulate up to 6 seconds and we run out. It just takes too much resources. But you can see up until that time, our model and the supercomputer model match very well. Okay, so that's why we can use this model to simulate out for a long time and get very accurate results. This is another plot that shows the overlay between what our identification model says and what the supercomputer says, and they overlap. The red, the blue, and the green, they practically overlap. So it's very high fidelity, high quality models. This is another way to compare how good the model is using spectrogram, which is plot of frequency versus time. And in this sort of spectrogram images, our eye can very quickly see any differences in the signal because there's images. Our eyes are very good at picking out pictures in images. And you can see this is the supercomputer model, this is our system ID model. And the results are very good. They very good. They match almost perfectly using a test input that is not the input that is used in ID. So when ID into the ID, you always use some test input, and when you test it, you should test it not only with the input we use in the application, we should test it with an independent set of input. And this is comparison using a different test of input, and you can see it's matched very well. Now, next I'll show you the simulation of a person walking and running, so you can see how the signal propagates throughout the space. See, he's walking, but now he's not running. Okay, so that's the typical model. And now I want to talk about inverse model. So what's the inverse model for? Well, to remind you, forward models describe the dynamics from a source to output, okay, input to output. That's forward models. Reciprocal models describe relationship from millions of possible source location to a single sensor that located at at the sensor located at regional source location in the forward model. That's the reciprocal model. And now, inverse model, what it does is that it figures out what the input signal is, given the measured output signal. So I have the output measurements, and I want to find out what the source